I'm going to be doing problem 51. So it starts off with a test rocket being fired vertically upward from a well. And a catapult at the bottom of the well gives the rocket an initial speed of 80 meters per second. So we're going to first draw the rocket being fired upward. So this is x equals 0, and since it is being fired by the catapult, it has an initial velocity of 80 meters per second. It accelerates upwards at 4 meters per second. So the acceleration here is 4 meters per second, meters per second squared, until it reaches an altitude of 1,000 meters. At that point, the engines fail. So here the engines fail, and then the rocket goes into free fall. So its path will look something like this, where this is the height of its path. The acceleration when it goes into free fall is the acceleration of gravity, which is negative 9.8 meters per second squared. So the first question is, for what time interval is the rocket in motion above the ground? So first we want to find the velocity that the rocket has when it finishes accelerating and gets to this point here. So this velocity. So to do that, we can use this kinematic equation, velocity final squared equals velocity initial squared plus 2 times the acceleration times the distance traveled. So velocity final is equal to the square root of velocity initial squared plus 2 acceleration times the distance traveled. And so the initial velocity is 80 meters per second, so 80 meters per second squared plus 2. The acceleration is 4 meters per second squared, and the distance traveled is 1,000 meters, so 1,000 meters. And if you calculate that, it will come out to 120 meters per second. So here means the velocity here is 120 meters per second when the engines fail. The next part of this would be to find the amount of time that this took for the rocket to accelerate all the way until the engines failed. So to do that, we can use this kinematic equation, x equals x initial plus velocity initial times time plus 1/2 the acceleration times time squared. So we know that the rocket traveled 1,000 meters here, so 1,000 meters, and this is where x is 0, so 0 meters. The initial velocity is 80 meters per second, and we're trying to find the time, so t plus 1/2 the acceleration is 4 meters per second times t squared. T squared. Whatever. There we go. T squared. So simplifying, you would get 2t squared plus 80t minus 1,000 equals 0. T squared plus 40t minus 500 equals 0. Put this into the quadratic equation and you'll come out with t equals 10 and t equals negative 50. You can't have a negative time, so you can cross out that answer, and you'll figure out that this distance traveled took 10 seconds. So t here equals 10 seconds. Okay, now that you have that, you will want to find how long it takes for the rocket to get to this top point where it is 0 meters per second, because in free fall, the height of the rocket's path will, the velocity at the height of the rocket's path will be 0 meters per second. So you want to find how long it takes for the rocket to decelerate from 120 to 0 in this area here. So to do that, you can use the kinematic equation, velocity final equals velocity initial plus acceleration times time. So you're trying to find the velocity here, 0. So the final velocity is 0 meters per second equals the initial velocity, 120 meters per second, plus the acceleration, which is gravity, so negative 9.8 meters per second squared, times time. You can simplify this, and you can have 9.8 meters per second squared times time equals 120 meters per second. And then if you divide that out, you'll have time is equal to 12.24 seconds. So this time right here is 12.24 seconds. So if you want to add that up, that's 22.24 seconds for this whole upward motion part. So now we need to find the downward motion part. Okay, now that we found all of this, we will want to find the total distance that the rocket traveled from here to here in order to help us find the total time that the rocket will travel falling down. So to do that, we can use this kinematic equation, x equals velocity initial time plus 1/2 acceleration times time squared. And so the initial velocity was 120 meters per second times 12.24 seconds, since it took 12.24 seconds over here, plus 1/2 negative 9.8 meters per second squared, since the acceleration is the acceleration of gravity, and the time is 12.24 seconds squared. Calculate that all out, and you will get 734.69 meters. So here up in the diagram, you can see that this distance here is 734.69 meters. So if you add that together, you'll get that that is 1,734.69 meters there. And that's also the amount of distance that this rocket will have to travel on the way down, 1,734.69 meters. So since we know that that's the distance it has to travel down, and the acceleration is 9.8 meters per second squared, because that's gravity, we can go ahead and use this kinematic equation, x equals b initial t plus 1/2 a t squared, to find the amount of time that the rocket will take to go to the bottom. So 1,734.69 meters equals, so in it's starting up here where there's the velocity is 0 meters per second. So the velocity here is 0 meters per second times t plus 1/2 negative 9. Here, here the acceleration will be just 9.8 meters per second, because although gravity is downwards, we're setting this is the positive direction since it's going downwards, and you're just trying to find the time, and we don't want to have a negative under the square root. So here it's just 9.8 meters per second squared, and then time squared. This is 0, so then time is equal to the square root of 1,734.69 meters over 1/2 times 9.8 meters per second squared. This time will then be 18.81 seconds. So the rocket will take 18.81 seconds to fall down from the top of its path all the way to the ground. Alright, so the first question is for what time interval is the rocket in motion above the ground? So we have that the rocket was in motion for 10 seconds here, 12.24 seconds here, and 18.81 seconds over here. So adding that all together, 10 seconds plus 12.24 seconds plus 18.81 seconds equal to 41.05 seconds, which is approximately 41 seconds. Okay, so the next question is, what is the maximum altitude? Well, we already found that out over here in the diagram. The rocket traveled 1,000 meters here and 734.69 meters here. So the maximum altitude is 1,000 meters plus 734.69 meters equal to 1,734.69 meters, or approximately 1.7 kilometers. C, what is the rocket's velocity just before it collides with the Earth? So for this, we have all this given information that we've already found out here, and we can use one more final kinematic equation, velocity final squared equals velocity initial squared plus 2a delta x. Velocity final equals the square root velocity initial squared plus 2a delta x, and plug in everything that we know. 0 squared, because we're going from up here. So since it's 0, and then we're just trying to find the velocity that it gains going all the way down until it hits here. So that's why the initial velocity is 0, plus 2, the acceleration is gravity. And again, since we're defining this as positive and this is negative, we can disregard the negative sign on gravity here. 9.8 meters per second squared times, and the distance that it travels is what we found previously, 1,734.69 meters. Calculate that, and the final velocity is negative 100, there's a square root, so 184.39 meters per second. And since the velocity is downward, in the downward direction, it's negative 184.39 meters per second, since negative denotes the downward motion. So that is how you do number 51. And this rounds out to negative 184 meters per second.